Okay, so hopefully that is coming through. Okay, so yeah, okay. So what I'm going to do is the first talk is really just to talk about what the challenges of parallel I/O, what the problems we'll kind of solve are, and I'll introduce a kind of the kind of prototype problem. It's a very simple parallel I/O pattern, but it was serve as a useful model for discussing the issues that we're going to have. So I'll cover why I/O is difficult, why parallel I/O is even more difficult, the kind of solutions that people do in parallel, and then I'll talk a bit about what is parallel I/O trying to achieve. I'll talk about files arrays and MPI-IO. This course grew out of a course which was specifically on MPI-IO for parallel I/O, but we realized over the years that over the lifetime of the service that people were more interested in sort of higher level things in other libraries. So I still do talk about a little bit about MPI-IO in some detail, because it is, we'll see, it is the lowest lying I/O layer that a lot of these libraries use. So understanding MPI-IO, how it works conceptually, is useful, but I won't go into any of the particular details like I used to, so we'll skip over some of those details. So why is I/O hard? I/O is hard because, you know, when you write a program, you have this nice process memory model. You launch a program, you have, or in parallel program, you have multiple processes. They all have access to their memory. When you do I/O, the data in memory has to physically appear on an external device, and that is, you know, an issue. You know, really have to get this data, which is stored in the memory of your parallel computer, or just in general of your computer. This is even in serial I/O. It has to get onto a physical external device. Files are very restrictive compared to data arrays. We'll see random access is very inefficient. You can skip around access a data array, a 2D array in memory quite at will, whereas files very much have a linear access thing. If you're seeking around to different places in the file, it's very inefficient. This linear, you may have to remap your program data. Your program data may have to be remapped and altered to be sensible to write to file. Any system you have, any language you have, has a huge number of different system-specific I/O calls. There's lots of different I/O formats. You can have text, binary, I/O floating-point numbers in big or little endian. Fortran unformatted is a nightmare. We have these libraries, HDF5, NetCDF. So there's a lot of different file formats to worry about. Disk systems are very complicated. We have things like RAID disks, redundant array of inexpensive devices. We have multiple disks. There's many layers of caching in memory. So it's really quite complicated. I think I/O is the HPC equivalent of printing. You buy a new laptop, you know, it works out the box, and then you try and connect it to a printer. You try and get the data from the memory of your laptop to an external physical device like a printer, and it all goes wrong. I/O is really, you know, is like that. It's really quite difficult. And this is going to be my prototype problem. Let's imagine that we have we've written a program, a serial program, and we have a 4x4 array of doubles. So you can see here, we have double X 4x4. Okay, and of course, if we have the 2D array in memory, in reality, it's just well, at least the way I've defined it here, it's just a single. There's a mapping from the 2D array to the linear space of data. So the way I've drawn it here, you can draw it many ways, but I'm saying we have a 2D array, 4x4, and in memory, the data is laid out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we actually get an array. What we really have is an array of 16 numbers. Now, the coloring here is looking forward to when we have this in parallel. You can ignore the coloring for a moment. And if I wanted to write this in serial, I would just say fwrite x, size of double, 4x4, to my, assuming I've previously opened the file. So I'd open this file, attach it to a file pointer, and in C, I just use fwrite and write this out. And this data on this 2D data array would appear in a file just as the linear stream of 16 numbers. And already you see there's a problem, because if I just do this, I've actually lost the information in the file that this was a 2D array. But I'll come back to that. But that's how I would do serial I/O with 4x4 array. Okay. And that's going to be my prototype problem. But what we're going to say is, in the future, well, we're not going to imagine this is a serial array. We're going to imagine it's done in parallel, that this 2D array is distributed across 4 processors. yellow, blue, green, and red, and how are we going to achieve this IO pattern here in parallel. And you can see that even with this very, very simple problem, if we were to split this 2D array up in parallel in this very simple 2D decomposition, let's look at the red process. The red process already has to write to different locations in the file. So even a very, very simple parallelization of a simple problem can lead to IO patterns, which are quite complicated, where you have to merge data from different processes. And that's going to be the challenge. So, okay, how are we going to do parallel of a 4x4 distributed array? Okay, if I wrote a parallel program, each process, say an MPI, would have its own 2x2 array. So process 1, process 2, process 3, process 4 would each have their little array of 4 doubles, which we're thinking of as being a local 2x2 array. How do we achieve for this data to be written out into this format, which is the same, which is the same as the serial format? Okay, the yellow data, the blue data, the red data, and the green data written out in their correct place. How do we do that? Okay, so what we're going to do is we're going to insert magical parallel IO call here, which is going to take the data from these 4 different processes, which are potentially running on 4 different computers, on different nodes, connected by some network, onto an external piece of storage. So it's written like this. So you can see already, even for what looks like a fairly trivial problem, a 4x4 array on a 2x2 grid of processes, we have a potentially quite complicated IO pattern here. Quite a lot of things to manage. So the naive solution is we have the array, we have all processes open the same file. Each process seeks to the right place and writes. So what I'm saying is we all write, all these 4 processes open this file, and rank 2 says, well, I'll skip to this location here, write this data, then I'll skip to this location here, write this data. So in principle, that looks like it's going to work, but there are problems with this. First of all, the performance would be poor. Okay, what you're doing here is each process is doing a series of skips and writes and skips and writes and skips and writes, and a real problem, you'll be doing thousands of small writes. We'll see that that disk systems, IO systems, are not well suited to a large number of small write operations. You want to do a small number of large write operations. You want to say, please write 2 gigabytes of data, not thousands and thousands of writes of kilobytes of data. But in fact, this won't work in general because multiple processes writing to the same file is problematic. Now, modern file systems may sort this out, but the problem in principle is illustrated by the next slide. Sorry, by a slide in a few. So I'll illustrate this problem. This multiple processes writing the same file is problematic. Okay, Unix doesn't really like this. When you open a file, the file system, Unix, thinks that you're the only person that you have the file open and nobody else does. What we're going to have here is we've said that lots and lots of processes should open the file, and that is going to be an issue. Why is parallel? So I've talked about why IO is hard. Why is parallel IO hard? Well, I've said here, we cannot have multiple processes write to a single file easily. General Unix can't cope with this. Modern file systems may be able to fix it up. But the reason is that, and I've got a diagram later on, that the IO is very slow. Okay, writing to disk is very slow. And so the way we make it fast is when you write to disk, you don't actually write to disk. You write to some local cache in memory. So in fact, IO to disk is cached in units of a disk block, which is about 4 kilobytes typically, maybe larger on a parallel file system, but on your laptop, it's probably 4K blocks. And these are not kept coherent. Okay? I'll discuss this on the later. So you might say, surely I can just have this IO pattern here. I've said all processes open this global file, and they all just write to their particular place in the file. You might say, surely this is okay, at least in principle, because they're writing to distinct locations in the file. That, in fact, could be problematic, and I'll explain why. Even reading can be difficult. You can say, well, surely each process reading its own section of the file is going to be fine. Well, if you run a program on 1,000 processes and open a file from 1,000 processes, the file system sees 1,000 clients opening the file, and that's going to overload the file system. The file systems weren't written to have thousands and thousands of processes reading or writing to the same file at the same time. It's just not going to, we'll see later that can overload the file system. And also the data is distributed across different processes. So as we've seen here, parallel IO is hard because even for a simple program, the processes do not in general own contiguous chunks of the file. This process here, the green process, owns distributed, it is in charge of or wants to read or write a small number of fragmented areas of this file. And that is something which is quite difficult to cope with, at least by hand. So we cannot easily do linear writes. We can't just say dump your data to file. We're having to do lots and lots of small files. And in reality, your local data may have halos. In parallel, we often have junk data. Our files are our local arrays are larger than they need to be because we might have halo data, and you have to strip these off. And so there are a bunch of issues which makes parallel IO even harder than serial IO. Serial IO is a bit of a nightmare. Parallel IO is even harder. So this diagram just illustrates the issue with simultaneous access. And it's just to show you what the problem in principle is. So imagine I have two processes, process 1 and process 2, both wanting to access a file. And you can think of these processes running on different nodes of a parallel computer or even on different people's laptops, but they're both attached to the same. These are different, think of these as MPI processes running on different nodes of a parallel computer, all wanting to access the same file. So they want to read the same file. So let's imagine that the file occupies 3 disk blocks. So a disk block is the minimum. When you read a file, even if you read 1 byte, the minimum transaction you can make is 1 disk block. Okay, and it's just like caching in a memory system, but it's there are issues with it. And typically this might be 4 kilobytes. So imagine that process 1 wants to access the file. So what it does is it issues. Process 1 has a disk cache. So whenever you read data from a file, it will be placed in a local disk cache in memory. In fact, Linux tends to reserve all the memory you're not using as a disk cache. So process 1 will have a disk cache, which is enough here for 2 blocks of the file. Process 2 has its own disk cache. Okay. So first of all, we read the file. So process 1 wants to read this data. Okay, it only wants the first half of the file. But your minimum IO transaction, your quantum of IO is a disk block. So it has to read in 2 disk blocks into its cache. That's the minimum amount of data it can read. 2 4K disk blocks, that's enough. And so does process 2 does the same thing. And then process 1 gets its data and process 2 gets its data. That's not a problem. You know, process 1 has a copy of disk blocks 1 and 2 and has loaded disk block 1 and half of disk block 2 into its array, into its memory, and process 2 has wants to have the second half of the file, so it's loaded disk block 2 and disk block 3, and then loaded some of that into memory. You now update that data. You update that data, and then later on you want to write to file. As I said, when you write to file, you don't really write to file. Writing to file is slow. What the operating system will do is it will stick it in memory just for the moment. So if I say I want to write this data to file, what will actually happen is it will be written to the disk cache, and then so will process. At this point, everything is fine. However, at some later point, you're going to want this data to actually appear on disk. At some later point, the operating system is going to have to say, well, actually, I do actually have to get rid of this data. David actually wants it to appear on disk. So I will flush my disk cache to disk. This might happen when your program ends, or it might happen because it thinks it's run out of memory to cache. You don't know. And this is why it's very dangerous to pull out a USB drive halfway through running a program, because if you're writing data to the USB drive, the operating system probably doesn't write data to the USB drive, probably caches it in memory, thinking, well, when I do a clear up, I'll flush the data to the external device. If you've pulled the USB device out, then the data won't be there. But if we look at this case, process 1 flushes its data to disk, process 2 flushes, and we get garbage here, because process 1 believed it was the only process accessing the file. Process 2 believed it was only the only process accessing the file. So that this caching will work happily if you're the only person writing the file, but if multiple processes open it, then in principle there's a problem. This is solved. I said this is like memory caching. This is solved in memory, because in memory we have at the point when process 2 modify this second disk block if this was memory caching in a shared memory system, there would be some cache coherency mechanism to notify process 1 that this data was now out of date, and it would need to get an update of the value from process 2. But file systems tend not to be coherent in that way. So there is in principle a problem here. In practice, it may be solved by locking or such like, but there is in principle a problem here because of the way that file systems work. So this might actually be solved by a parallel file system doing locking, but that would then serialize the I/O. So the naive solution number 1 of everyone opening the same file and writing to it is not a viable solution for a number of reasons. So the next thing people do in parallel is they do independent I/O. They do file per process. Each process opens its own data file and writes its local data. So this is very simple to implement. Okay, it's very, very simple to implement, but it is a nightmare to cope with in practice. This is the kind of thing people do when they're developing a program on their laptop. You maybe run on 10 or 20 processes, you end up with 10 or 20 files. Once you start running at scale on thousands or even tens of thousands of processes, you end up with thousands of files, and this is just very difficult to cope with. Often requires a lot of pre and post processing. And here, your data format depends on the number of processes. Okay? What I'm saying here is if you ran the program on one process, you get a single file of 16 doubles. If I ran it on 4 processes, I get 4 files each of 4 doubles. I find this philosophically not acceptable. Parallel computing get you the same result but faster. Okay, so although file per process independent I/O is something which it's people's typical first approach to parallel I/O, there's a whole bunch of problems with it. First of all, you need a lot of pre and post processing. So this is what you would do. Okay, you just basically everyone defines their own local file, which one we call data1.dat, data2, data3, and data4. We just write our local data and we end up with 4 files. That is problematic to me because afterwards if you do any post-processing, we have to reassemble these data files back into the original format, which can be difficult. Dealing with tens of thousands of files is very problematic. So this is what we want to achieve. Okay, we want to achieve parallel data written in parallel to a single file, where the data is written out to file in the same order as the serial program would. Okay, so we get the same output, the same file on disk as we would in serial, but we get it faster. So another solution which people use is called controller I/O. What we do is we send all the data to and from a single process. So people often nominate rank 0 in an MPI program as being the controller. What you do is when you want to read the file, rank 0 reads the data and then scatters it to all the other processes. And when you want to write the file, rank 0 gathers the data together and then writes it as a single write. So the main advantage is the output is the same as the serial So we get the same output in our parallel program as our serial program. However, there are 2 issues with this. First of all, we quickly run out of the memory on the controller. What we're saying here is the controller process has to be able to store all the data, the entire parallel simulation data in its memory. That's unlikely that you can do that. Typically, each process on ARCHER2 has a few gigabytes. Your data set's going to be much bigger than that globally. So then you have to write out in small chunks, which becomes difficult to manage. But we'll see later the performance is poor. Only a single process is writing, and this is a serial solution. We get no benefit from parallel file systems. We'll see later that parallel file systems require many processes to be writing at the same time to get performance. And so, although the file per process approach has many processes writing at once, it gives us lots and lots of thousands of little files, which is a bit of a nightmare to deal with later on. The naive solution of controller I/O does give us the correct output, a single file, but the performance is poor because the I/O is performed by a single process, typically rank 0. So what we want is a way to do parallel I/O properly. We want the I/O system to deal with all the system specifics, but we want to get we want to end up with a file which is identical to the serial file. As I said, all files should have the same format as the serial file. the entries should be stored according to their position in the global array. You might say, you know, well, you said that the problem with so I'm coming back to this. Apologies. I said that the problem with this is that we have lots and lots of little portions. Well, why can't the yellow process write the first 4 elements, the blue process the next 4, the green process the next 4, and the red process the next 4? Well, the problem there is, although we're doing large I/O transactions, again, the layout of the final file depends on what your decomposition was. It depends on how you parallelized your program, which is not really an acceptable situation. So the problem there with animations is we have to skip them. So back to, okay. So a number of libraries exist. I'll consider MPI-IO first for 3 reasons. One is A, I understand it probably better than the other ones. B, the conceptuals, the way that MPI-IO works conceptually is the same as the way that most other libraries work. They have different approaches in practice, but in principle, they're doing the same thing. And thirdly, a lot of I/O libraries, for example, HDF5, call MPI-IO at the lowest level. So if you understand how MPI-IO works and how it gets performance and what the good and the bad things are to do with MPI-IO, you understand a lot about other I/O libraries because they tend to layer on top of it. So, you know, the fundamental difference between parallel I/O and serial I/O is that in parallel I/O, you have a lot of processes that own their own data. You need to tell the I/O system how these local arrays should be stitched together. You need to say, look, I'm process 3, and that I own the top right-hand corner of the data. Okay? That is not required in serial because a single process owns the entire data. In parallel, you need to tell the I/O system where to put the data, which portion of the global file each process owns. Unfortunately, the mapping from that local to the global data is just in the mind of the programmer. We may imagine the process is arranged in a 2D grid, but when you're running an MPI program, as far as the computer is concerned, as far as ARCHER2 is concerned, you're running thousands and thousands of separate processes all doing their own thing. So the crucial extra step in all parallel I/O, and the details differ from library to library, is we have to describe the data layouts of the I/O system. We have to tell the I/O library what portion or portions of the global file each process owns. And that is the crucial thing we have to do. So, as I said, the programmer view is that you have 4 processes working together on a big problem where the red process owns the top right-hand corner, the blue process owns the top left-hand corner. But as far as your machine is concerned, it's running 4 processes, each of which has an array of size 4. So this is just in your mind. You need to tell the I/O system additional information, how that this red data should be stitched together into the top right-hand corner here. So the way I think about it is that think of the file as a large array, okay? In some sense, imagine we're recreating a single large array on a controller process. Imagine that you're so if you do controller I/O, where the controller process grabs the data from all the workers, the controller process needs to know where to put the data. So it's stitching all this all together into a large array, and then it writes it to disk. What you want is an I/O system which does this, an I/O library or system which does the same thing. It creates this array and saves it to disk without running out of memory. I am never actually doing naive controller I/O. So the way you think about it is, imagine I'm doing naive controller I/O. I'm recreating the entire file on a controller process. How does it need to be stitched together to create this array? But we don't actually want to do that. We want to do it more cleverly than that. We also want to do a small number of large I/O operations. We want to merge data to write large contiguous sections at a time. And I'll come back to that. But what you want is the I/O library to recognize that you have some scattered data, which merges together into one large block, and to write that out as a single write. You want to do a large number of small I/O operations. You also want to use any parallel features of the file system if the file system can cope or benefit from multiple simultaneous writes. If there are multiple I/O nodes, and we'll cover this in the next lecture, you want to do that. And you want it to manage any of these nasty coherence issues with file blocks. If 2 processes are writing to the same file block, you want it to manage that in a clever way. So the MPI-IO approach, MPI-IO is part of the MPI standard. and each process needs to describe what section of the global array it holds. Now, it's up to you to get this correct. It's up to you to describe this correctly. But what you do in MPI-IO, and this is generically the same for all I/O systems, you open the file, you tell the library which portions of the file or subsections of the file each process owns, then you write the file and then you close it. So open, write, close is standard. The extra step, which is crucial in parallel I/O, is telling the I/O library what the mapping is from your parallel program to the serial to the file. So what you want to do is you want in some way to tell the I/O library, look, I'm process 3. I have 4 elements. They're the bottom right-hand corner of a large array. And MPI-IO does this using derived data types. Now, I'm not going to go into this in detail, but just to say, MPI-IO uses derived data types, which you may have come across, to do that. So it hijacks, in some sense, that technology to do this description of. So MPI derived data types allow you to have data types which are subsections of large arrays, scattered data types which aren't contiguous in memory. That allows you to tell the I/O system, look, my green data isn't a contiguous section. It's elements 9, 10, 13, and 14 of the global data. So other parallel I/O libraries exist. MPI is usually the lowest one. You may never call it directly, but I do cover it, not at least on its own, because it's probably the most important one, the common one. Higher level libraries exist. The benchmark we're going to be running will allow you to do HDF5, NetCDF, or ARCHER2. But the approach is the same. There is some way in these libraries we're describing what portion or portions of the file each process owns. And actually, a lot of these libraries then actually use MPI-IO to do their actual reads and writes. So that's the way it's going to go. So summary, parallel I/O is difficult in theory and in practice. MPI-IO provides a high level abstraction, where, as I said, you use derived data types to describe how your local data maps to the global data. MPI hides all the system specific details. It's portable to different systems, but hopefully at runtime takes advantage of whatever your local file system is to get good performance. We'll see MPI-IO is quite a raw format. It doesn't give you much help. There are a lot of more flexible formats which different communities use. NetCDF, HDF5 and NetCDF2. I'll talk about these in general later on. But as I said, they gain performance by layering on top of MPI-IO. If you're developing an HDF5 I/O library, you don't want to spend your time, you want to worry about HDF5. You don't want to worry about how does parallel I/O work on the system. So the MPI-IO people have worried about how parallel I/O works and solved that problem. So as an HDF5 library writer, you layer on top of that. MPI-IO requires a good understanding of derived data types. I'm not going to go into that in detail today, so that's just a general comment. So that's the end of the first talk, which is just a very general overview. Are there any questions? I will just put up the timetable just to show. Okay, just to check, just checking the audio is still okay. Good, okay, great. So I'm going to now talk a bit about parallel file systems and Lustre. So I remember parallel I/O has become an issue as machine sizes have got bigger and bigger. The number of CPUs, the number of nodes has gone up. And we first saw that really on the Hector system, which was we were involved in, which we hosted well over 10 years ago. And we had to find out about parallel file systems because users were starting to have issues with I/O, which hadn't been a problem on previous systems. And I realized I didn't actually know what a parallel file system was. People said, I've got a parallel file system. I had no idea what it was. So hopefully this will explain what parallel file systems are, and also how Lustre, which is very common parallel file system. So what parallel file systems are from a hardware level, and what Lustre is, which is the standard software level for accessing them, which is pretty universal now. So we'll cover parallel file systems, what Lustre is, what striping is, which is the key technique Lustre gets to get performance, Lustre uses to get performance. simple Lustre command, and I'll have a sort of I'll talk about conceptually what the bottleneck, given how parallel file systems work, what are the potential bottlenecks? What are the things which can slow us down? What are the things we're going to have to cope with or worry about when we're doing parallel I/O? So, just to go back, what is a parallel computer? People, in the early days of supercomputing, people thought that a supercomputer was something they could just stick their program on it, would run faster, but they're not. Supercomputers are parallel computers. They're actually constructed of many standard processors, each not particularly fast. Your laptop is probably faster than the nodes of ARCHER2. Sorry, the CPU core on your laptop is probably faster than the CPU cores on ARCHER2. But your laptop has 4 of them. ARCHER2 has 750,000. So performance comes from using many processors at once. But the corollary of that is it's up to you, the user, to manually distribute data and calculation across processes. It won't happen automatically. Somebody has to write the parallel program that distributes both the data and the calculation across these processes. So parallel, and the reason we do that is that we can't make processors any faster. Parallel file systems are constructed from many standard disks, each not particularly fast. It's difficult to make disks faster. The simple thing is to, rather than spending lots of money on slightly faster disks, buy lots and lots and lots of standard disks and use lots of them. So the performance comes from reading or writing to many disks at once. Each disk isn't particularly fast, but a parallel file system has lots of them. However, it's up to you to ensure that your I/O setup achieves that. So what you need is, rather than many processors doing calculation, you want many clients to read and write to different disks. So a parallel file system allows multiple people to connect to it at once. So it understands that not one processor or user is using it at once. Many people are, but each of them, it turns out each node on ARCHER2 is a client of the file system. What the file system in ARCHER2 thinks that ARCHER2 is about 6,000 separate computers numbered 1 to 6,000, all of which want to access this file system. But for you to get good I/O, you need to read and write at the same time to different disks. So each HPC node is a separate I/O client. We'll see that you might say, well, that's going to be a problem, because what happens if I only have a single file? Well, we'll see that data from a single file can be stored across many disks, and that's called striping. So that's the way that parallel file systems work. Under the hood, they have multiple disks, but they're also able to store a single file across multiple disks. However, that's going to be complicated. When I open a file, it might be stored across 20 different disks. Do I have to, when I do an ls, what do I see, 20 files? No. This must appear as a single file system to the user. When you do ls-l on your file, you should see a single file, despite the fact it's physically stored across lots of disks. And so typically there's a single database, a controller called the metadata server. It's effectively a database which understands where your files are stored. So there's a single metadata server, which is effectively a database, which stores all this information. So the way that parallel file systems work is that you have your parallel computer here. You have lots of processes running on your compute nodes, each with their own memory. And then you have multiple storage devices. And these are called OSTs, object storage targets. Now, I will call these naively disks. You might argue they're not disks, but to me, they're a disk. They're the minimum addressable thing you have. So your files are actually stored on multiple OSTs, which I think was being disks. Okay? You also have a metadata server, which is actually stored on a single metadata target, but that's not particularly interesting. We have a metadata server which understands the mapping from your program to these. So there's two issues here. One is when you write a file, where is it stored? There's lots of disks to write to. Which disk is it stored on? You don't need to remember that, because the metadata server, the database, has all that information. Or if you're writing a single file, which we'll see can be stored across lots of disks, you'll say, well, I'm writing a single file. Where is the 500th byte? Is it on this? The metadata server knows that as well. So in practice, the metadata server is stored on some hardware, a metadata target. This is all Lustre speak, but that's really not important. I think the most important thing about the metadata server. Also in practice, these object storage targets, these disks, are clustered together into servers, object storage servers. Now, again, the way Lustre works, you don't tend to see this level. So there is this hierarchy of application processes, a high-speed network which allows you to shuffle data around these different processes on ARCHER2. That's your slingshot network. And these abstractions of metadata metadata server and object storage servers, of which there are many, and the hardware devices, metadata target, and the object storage targets. I think the simplest way to think of Lustre is to think of the metadata server as being this database and not care where it's stored. But as a user, you interact directly with these OSTs, not with these OSTs. So I will talk about metadata servers and object storage targets, which I may call disks at some point, because to me, they're just multiple disks. So that's the way that parallel file systems work, and Lustre in particular has this naming terminology. So this is a picture of, I don't have pictures of ARCHER2, these are of ARCHER, but it shows you what it happens. On ARCHER, we had these boxes, each of which had multiple object storage servers, each with multiple disks, multiple object storage targets, and stuffed together in a huge rack. So you basically have this device, a storage device, which has lots and lots of separate computers. Okay, these are actually separate computers, each with lots and lots and lots of disks in them. So and we'll see on ARCHER2, we're talking about many tens, well, of maybe 50 or 60 separate disks. Now I don't have a picture of ARCHER2 storage, but it's quite complicated. But as I said, I think the important concept of the metadata server and the object storage targets. So terminology, I said, Lustre has these many different levels of virtualizations, but as I said, one object storage server can have multiple object storage targets. An object storage server is effectively a computer with its own operating system, but it can control multiple disks. And a single OST actually has many physical disks in an RAID array, multiple storage units for parallelism and for redundancy and error checking. But I think the simplest way to think of Lustre is the metadata server, the database that contains information on e.g. where a file is stored, and the object storage target, the physical device that stores your data, and I will call this a disk. Although it may contain multiple, I'll call this a disk. And the MDS and the OST are what a user interacts with. So that's why I think these are the most useful things to think about. So the ARCHER2 hardware, there are 3 separate /work file systems, work 1, work 2, and work 3. Each one has 12 OSTs, 12 disks, and 1 MDS. So you can see that, if we have 1 MDS and lots of object storage targets, the MDS is a central point of control. Okay, so anytime you open or close a file or do different kinds of disk access, you have to talk to the MDS, the metadata server, to find out where is this data stored on the physical storage targets. So that's potentially a bottleneck. So if you had one metadata server and lots of disks, you would be able to do very fast parallel I/O, but the metadata server, because you'd have access to lots and lots of disks, but the metadata server might get overloaded. All users will be accessing the same metadata server. If you have lots and lots of metadata servers, each with a small number of disks, then you're not going to overload them because users will be accessing different metadata servers, but each one won't be able to do very fast parallel I/O because they might only have a couple of disks. So the kind of the sweet spot in ARCHER2, which we've chosen, is that we have 36 object storage targets, 36 disks, but we split them to 3 different file systems, where each file system has 1 metadata server and 12 OSTs. And a particular project on ARCHER2, a consortium, is assigned to different partitions to share the load. So as a project, and we were a project with TA173 today for this course, we will be assigned to a particular metadata server, a particular work 1, work 2, and I don't know which one we're on. We are on well, we actually been okay. We're actually on work 4, which is a new one to me. That's interesting. So So we're actually on work 4. Okay, so this is that's news to me. I thought we had 3. There may be an extra one now. Okay, we'll find out about that. But we're actually on work 4. I'll have to update these slides. There's also a solid state storage system, which aren't spinning disks. That's built on the storage. So these OSTs are just classical disks like you'd have in an old-fashioned laptop, platter spinning round. We also have a system with solid-state storage built on NVMe, non-volatile memory, and we do have access to that for this course. You would expect this to have better latency. So one of the problems with doing small I/O transactions to a disk is there's physically a physical head, a physical read and write device which has to move over the disk. And that means that doing a large number of small I/O operations is very inefficient. With solid state storage, it's much more like memory. You can access data much more easily. There's no physical thing having to move around. And so we have access to that file system today. You may want to play around with it. Each has around about 3.3 petabytes of storage. This is the disk system, so it's 13.2 petabytes. Now, I'm not normally a pedant, but if you say gigabyte or megabyte, you're technically talking in powers of 10. So a megabyte is 1,000,000 bytes, a gigabyte is 1,000,000,000 bytes. If you want to talk about powers of 2, they're typically, we have this, a petabyte is not the same as a pettybyte or kibibyte or a mibibyte, whatever how you pronounce it, which is actually powers of 2. So we have the reason I say is I couldn't work out why I thought that we had 13.2 petabytes and the disk, the documentation says 14. That's the difference between powers of 2 and powers of 10, which get quite significant at this level. So we have tens of petabytes of storage split into 3 systems, each with 3 or 4 petabytes of storage, each work 1 work. And I will find out why we're on work 4. I didn't know about that file system. So what happens by default? Well, by default, if you open a file, it's stored on a single OST. So if you open a file, the metadata server, you want to say, I want to open a file, the metadata will pick an OST to stick it on based on which one's freest, which one's got the lowest load. You don't know which, but by automatically, individual files by default will be distributed across the OSTs. You can see we immediately got some parallelism there for no extra work. So by default, each file is stored on a single OST and automatically distributed across the OSTs to balance the load. In fact, each OST is a separate Linux file system. If you went onto that Linux file system, you would see your file there. So this is called an unstriped file. We'll see that striping is where you store a single file across multiple disks, multiple OSTs. By default, at least on ARCHER2, each file is stored on a single OST, but if you open 10 files, they will be stored across different OSTs. So reading and writing multiple files from multiple nodes can benefit from multiple OSTs. If we opened a different file from each of these processors, each of these nodes, they will be distributed across different OSTs. So we would get parallel I/O, we're reading and writing to multiple disks at the same time. So that is why file per process, at least up to a certain scale, does work on Lustre, at least from a performance point of view. So reading and writing multiple files from multiple nodes can benefit from multiple OSTs, but access to a single file will not benefit from the parallel nature of the file system. So you'll see that if you're reading and writing to a single file, which is what controller I/O does, you do not benefit from the parallel the disks, because the single file by default is stored on a single OST, a single disk. These disks are not particularly fast, while the NVMe ones might be, but the standard ones aren't particularly fast. And so we'll see that this is not. So I'm saying here that to benefit from the parallel file system, you need to read and write multiple files. I've already said that file per process, multiple files is difficult to cope with. But I've just said here that access to a single file will not benefit from the parallel nature of the file system because it's stored on a single OST. So how are we going to square that circle? Well, Lustre allows you to stripe files. So you as a user see a single file, bigfile.dat, but under the hood, the operating system or the file system divides the file into stripes if requested by the user. So you can say, this is a big file, please store it across multiple disks. And Lustre will by default store it across 1, 2, 3, 4, 5, 6, I've got 7. We'll split the file into sections to multiple disks. So when I read it, if I do large I/O transactions to this file, I do a big write, they will be split across different disks. I can benefit from the parallel file system for a single file if I take advantage of Lustre striping, if I ask Lustre to tell it to store the file on multiple OSTs. So striping is the fundamental way you get parallel performance for reading and writing to a single shared file. So striping allows multiple I/O processes to access the same file, and it increases the bandwidth as you're accessing multiple OSTs. Again, like all files, so this is optimized for bandwidth, not latency. Reading and writing small amounts of data was very inefficient. It's already inefficient on a single disk. If you want to write 1 byte to a certain position in a file, you're going to have to ask the metadata server, I'd like to open this file, I'd like to write to this particular byte. The metadata server, I'll say, okay, so that wants to write to byte 1,000,000, so that's byte 7,000 on OST4. There's a huge amount of processing goes on. Everything here is designed over a small number of large I/O operations, okay? Not a large number of small I/O operations. This is called striping. Striping is fixed when a file is created. That's under the control of the user. And the fundamental parameters are the number of stripes and the stripe size. So, if you imagine, if a file was striped in the way that this diagram illustrates, where the file was split into contiguous blocks, that's not going to help, because if I write, here, if I write a significant fraction of the file, the first 8th of the file, for example, it's all stored on the same OST. Okay, it's not going to help with parallelism. The way that striping works is it tries to distribute the file across as many disks as possible. So it's not a block decomposition. What it does, if you create a file with a stripe count of 4, okay, so you can tell Lustre, I would like this file to be created and stored on 4 disks. That's called a stripe count of 4. Lustre will assign 4 OSTs, say OST 1, 2, 3, and 4. And it's not the first quarter of the file is stored on OST 1, the second quarter on OST 2. There's a stripe size, and the stripe size is by default 1 megabyte. The first megabyte is stored on OST 1, the second on OST 2, the third on OST 3, the fourth on OST 4, and the fifth back on OST 1. So you can see if you do any I/O transaction of 4 megabytes or more, it will access all the OSTs, which is what you want. So it's round robin, and the default stripe size is 1 megabyte. You can change that, but we found that it's typically that seems to work. So I see a couple of EPC people who have joined. We're running maybe about 10 minutes late. So Rui and William, we will start the exercise maybe a bit late, but we'll start it before 11. Sorry, I'm running a bit late. So the Lustre commands to set the stripe on a directory or file, you do LFS set stripe, and you give it the number of stripes. You can say -1, and that just says stripe it across everything, and that means -1 on ARCHER2 corresponds to 12 OSTs, at least on the disk file systems. You can set the stripe size, LFS set stripe -S4 megabytes, but I've not found that useful in practice. This does not alter the striping for existing files. That requires a copy. So, when you set the striping on a file, that is set for the entirety of its life. I tend to set you can set the striping on a file or a directory. I tend to set the striping on a directory. I say, look, I'm going to do large parallel I/O for this program. It's all going to go to the output directory. I will set the striping on that directory. All files subsequently created in the directory will have the same striping. So that's the way the exercise works. You can inquire about a file with LFS get stripe. So parallel I/O to a stripe file is very complicated in practice. Where in the file does the local data need to be written? Which OSTs is the stripe located on? Are there write conflicts from different processes? We need to use a parallel I/O library to do this. And so I'm now going to talk. So we're going to talk about that later on. But what I want to now just conceptually is to think about where are the bottlenecks in this system. We have multiple processes or potential writing at the same time. There is a network to route all those I/O requests to these disks. We have multiple disks with a single metadata server. Where could the bottlenecks possibly be? I'm going to use an analogy of people leaving a train. So I quite like analogies. You may not, but this is mine. So I got a train analogy. So these train carriages are our multiple compute nodes. So we have 4 compute nodes. Each compute node has multiple processes on it. So and those are these, I've represented them by the exit doors from each carriage. So the carriages represent the compute nodes. The exit doors represent multiple processes writing from those compute nodes. So here we have 4 compute nodes, and we've got 8 processes writing, 2 from each compute node. The platform is like your network, it allows people to move about, but the platform has a limited number of exit doorways. And these exit doorways, I think of as being this is the file you want to write, but these are like your OSTs, okay? Basically, these are the multiple endpoints that you're trying to access. They're multiple doors. So in this train analogy, which hopefully is useful, the carriages represent the compute nodes. The doors on each carriage represent having multiple processes writing from each compute node. And these exit doors here from the platform represent multiple OSTs. So if you just think about this train analogy, you can immediately try and envisage where the bottleneck's going to be. Is it going to be here, 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 here? Well, let's look at one example. A serial exit door is where you store the file on a single OST. And what you see here is it doesn't matter. This is if you store the file on a single OST, if you have a serial exit door to your platform, it doesn't matter how many nodes you have, how many people you have writing, how fast how capacious your platform is. It is going to be limited by everyone is going to be queuing up to exit the platform through this single door. So if you have a file stored in a single OST, if it's not striped, that's like having a single exit door to your platform. That is going to be the bottleneck. People are going to be able to leave the train very rapidly, but then they're going to have to queue up to access this exit door. So that is showing you that if you don't have parallel storage for your files, there's going to be a bottleneck at the very end point. Accessing the file is going to be the bottleneck, like having a serial exit door from your platform. What happens if we have a serial train door? This is like controller IO. What you say is I have lots and lots of nodes and lots of processes on each node. I'm going to do my IO from a single process, rank 0. So everyone has to run all the way down the train to this. Here, it doesn't matter how many exit doors you have, okay? The bottleneck is people leaving the train. So if you only open one door on your train, this is equivalent to controller IO, the bottleneck is going to be people getting out of that. It doesn't matter if you have multiple exit doors. It doesn't matter if you store your file on multiple OSTs. You simply can't get people off this train fast enough. And that is controller IO. We will see that for controller IO, you do not benefit much from striping the file because the bottleneck is just getting the data off of that single process. We could have reduced train doors. We could say, well, what we're going to do is we're not going to have a controller IO. We're not going to do all the IO from a single process. We're going to do the IO from one process on each platform, on each node. Apologies, one process from each node, and we're going to have a parallel storage of the file. We've got 4 exit doors. So it's not clear here. The question here is, where is the bottleneck? Okay. The question here is, can we disembark people from each carriage quick enough through a single door? So remember, people still have to queue up on a carriage, okay, to get out this door to saturate. So it's not clear here, and we'll look at this in parallel. In this setup, is there enough parallelism here? Do we have enough exit doors from the train to saturate? Or the question here is, can people exit the train door faster or slower than they can leave the exit door? Okay, and well, actually, this is the setup on the way that MPI-IO works on ARCHER2. It says that for each node, I will allocate one IO process per node, and I'll allocate the same number of IO processes as I have OSTs. I will open same number of doors on the carriages as I have exit doors on the platform. It's not clear on this setup what is going to happen. You might say, well, let's open more doors on the carriage. If the bottleneck is that if the bottleneck is this door here, we're not actually getting enough people on the platform to saturate the exit doors. You might open multiple doors on each train, which is the original diagram. The worry there is you might have too many people leaving the train carriages. You might have congestion on the platform. You might be overloading the network. Okay, I should have mentioned that on the first slide. So it's not clear if you want to have one door open per carriage to throttle how many people get out onto the platform, or multiple doors, in which case you may have too many people on the platform and you may get congestion on the network. So I think I find that a useful analogy. It's not clear if the bottleneck is going to be the network, the number of the speed at which people leave the carriages, or the speed at which people leave the platform. And we'll investigate all those situations with different I/O setups. So the obvious question are, if we're opening thousands of files, does the metadata server become overloaded? What's the maximum performance of a single OST? Can one process saturate an OST? Can a node saturate an OST? Is the network the limiting factor? How do different I/O libraries work? What's the best stripe count and size settings? These are all questions you might ask. To investigate this, I wrote a very simple benchmark to investigate Lustre performance called MPI-IO, and we're going to use this as the test case for our exercise. And all it does is it writes a large 3D distributed array of double precision numbers. It's exactly the same as my test case of the 2D array on a 2D grid of processors. It's actually a 3D array on a 3D grid of processors. It came from some work I did years ago for somebody. It's written in Fortran for historical reasons, because the program which the code I was helping the user with, a guy called Anton Sternlich, had a Fortran program. I do have a much nicer C version of the benchmark, but we can't use that for this course, unfortunately, because it was written by an MSc student who hasn't yet graduated. But once they've graduated, I will switch to this new C version. But it's written in Fortran, but purely for historical reasons. So we'll have 5 minutes. Just performance variability. Benchmarking I/O is tough. We share the HPC resources with all users on the machine, and we share the network bandwidth. We're all using the same platform. And so I/O results can be quite variable. You share the I/O reads, so you share the network with all users, you share the OSTs with all users, and you share the MDS with users on your file system. So at any one point, these can suffer from contention. So you can get slow results due to congestion. And that's possibly going to be a problem on this course, because we're all handling the file system at the same time, because we're all running these benchmarks. But performance is very variable. So a summary, a Lustre file system has multiple OSTs. I think of these being multiple disks. By default on ARCHER2, each file is stored on a single OST. That's called an unstriped file with a stripe count of 1. But you do get increased performance for multiple files because Lustre stores different serial files on different OSTs on different disks. So this is good for a single user writing multiple files, or for a shared system. On ARCHER2, we have lots of users. So if lots of users are each writing a single file at the same time, we do get some benefit from the file system, because those files will be distributed across OSTs. However, as I've said, a single user writing many files, if that's a file per process, you can end up with thousands of files, and that can overload. We'll see that can overload the metadata server. So to improve the performance for a single file requires striping, which is under control of the user. So you say to Lustre, I would like this file to be stored on all the OSTs, please. And then you hope that when you do parallel I/O from a parallel I/O library, it recognizes that and takes advantage of that. And that's how we're going to do what we're going to do with the benchmark. So I'll just, if there are no questions, please, if there are any questions, I will switch to just showing you. So I know now why I wasn't able to share my Chrome window, because it comes as a blank on Collaborate, but it is there, but it's a blank. That was my my problem. So what we're going to do is we're going to do the practical. So here's the parallel I/O exercise sheet, which is not being shared, is it? No. Okay, so I have to share that separately. It'll open in a different window. So what I really want to do is really so we're going to clone. This is the benchmark we're going to use. I can show you that on Lustre. But what I want you to do is basically to log on to ARCHER2. So what I want to do in this session, we've got a couple of people in case there's an issue. Could people now log on to ARCHER2 and just check they can log on and check that you can clone the repository? And actually, after that, we can take a break. There's half an hour after so we can start the exercise after the break. But the reason I just want to get people logged on before the break to sort out any login problems. So could people log in to their ARCHER2 account and check out this repo? I will. Show you. I'll switch to that window now. This is the repo. There is there's code here which you can just clone, but there is a little README which is maybe worth reading because it tells you how the benchmark works. I mean, I would just give you specific instruction how to run the benchmark, but there is some information here on how it works. There is the code, but for now, I just want people to log in and yeah. So William and Rui are here. So please, if people could log in, and I have a so what will I do? I will so I will just show you what I want you to do. Excellent. Okay, so I'll just so yeah, I'm going to SSH into so my account is called TA037DSH. That's I have at login.archer2.ac.uk. Sorry, TA 173, isn't it? 173. I've already logged in today, so it didn't ask me for my TP code. I want cd/work/TA073-TA073. Then your username, which for me is TA073DSH. You'll probably have a more sensible username. And it's because I've got this wrong, it's TA173, sorry. And now I can find out where I am. And we are on, I don't know if Rui or William knows it, we're on work 4. I've not really heard of work 4 before. But
it's one of the newer ones. I don't think it's been used until recently, so perhaps it's only newer projects on there.
Yeah, I'm surprised, but it seems to be size is 24.9 terabyte. I don't understand. Yeah, okay, yeah, I just yeah. So let's okay, so that's interesting. I will have to play around with this just to check that. So is it okay, but we will. Okay, so I think I saw. So all I want people to do is to log on just now and check you can clone. So Laura gets permission denied. So maybe we can. Can you? I'll maybe need to make. Oh no! Wait a second. No, okay. Okay. So so what? Yeah. So you yeah. So what's your? I think you're not in the right directory. If you logged in, that's fine. What directory are you in? What's your username? You should be in. What's your username, Laura? Oh yeah, yeah. Yeah. So if you look. You should be in, it's a bit confusing, /work/TA173173, and then that should be your username there. So if I do, I can see the other ones here. I can see, Yeah, that's you there, isn't it? So you should be in /work/TA173/TA173LB. Oh, these are, so yeah, I see a lot of people have this format. We suggest this to you now as a username, don't we? That I had forgotten that was a. Does that work now, Laura? Yeah, great, thanks. So it's a bit annoying when you log into ARCHER2, you end in /home, and you really want to do all your work in /work. If I have already cloned the directory, but I'll let's just do a git clone. You'll see that if you look at the instructions, apologies, I'm dotting over too many windows. You should be able to compile, but what we want to do is to set the striping. So I'll just, before we take the break, I'll just show you what I want you to do. It's in the instructions, but I want to do, there's a directory called full striped. It's just a directory. I want to make that, by default, that will be created with a LFS get stripe. And there's a README file in there. That is on a stripe count of 1. That's an unstriped file, okay? I want this to become a file to be created striped. So I will do LFS set stripe -c -1 on full striped. If I now touch, and that doesn't change the striping of the README, which is already there. It's still a stripe count of 1. If I create a new file, if I touch full striped /test.Dat, and I do LFS get striped on that, you'll see now it is stored on 12 across 12 OSTs. And so it's stored across OSTs 0 to 11. You'll see that the README was just stored on OST 6. So okay, I was just checking this because I wanted to check that we still had 12 OSTs on this file system. We do. So you can see the stripe count is 12, and the stripe size here by default is 1 megabyte. So as I said, the if anyone if you're having problems logging on, then let us know, but you should be okay. We're just, it seems to have gone quite smoothly. We're just 5 minutes late. So, I'm going to take a break now, but what you should be doing, I'll just basically read through the exercise sheet. Hopefully you can see that. Yeah. So I want you to, this is what we're going to cover. I want you to log in and go to your correct directory, clone the repo. You need to use some modules, and you should be able to compile. You need to set up some striping, and then you should be able to run. So I would very much appreciate if someone could at least just try running this job. So we have reserved resources for today, and I just wanted to check that they work. So if anyone is, I just want to check I've set that up correctly, because that should automatically submit. Okay, all right, good. Okay, great. So that ran, and so that's good. That ran correctly. Excellent. Okay, so that's really what we'll do is we'll get back. So that's fine. If everyone's on, you've managed to run. I haven't made any howlers like I usually do, except not knowing what work 4 was. We can come back at 11:30. So 11:30 till 12 is the timetable to be the exercise, and then the next lecture is going to be at. So it's in the exercise sheet. It's here. Yep. So you follow the Have you got the exercise sheet Carlos? And then you just follow through the instructions. Should be quite explicit, hopefully. Is that so? Yes, it's a bit confusing. Yeah, there are two repos. There's two repos, one for the course material and one for bench.io. Hopefully they're linked. Yeah. Okay. Okay, that's good. So that's gone reasonably smoothly. Okay, that's good. So I mean, we're slightly behind, but I had it timed like this so we would have a break. And the way that the timetable works is that I will put it up and we can come back. Okay, so goodbye. So I'll see you again in 20 minutes at 11:30. And we'll get back practical and we'll do the simple exercise. Sorry, we'll do the straightforward exercises on the sheet. And you probably want to read the bench.io GitHub to explain what the parameters and stuff like and what it actually does. But I have specific suggestions in the sheet.